Yeah, it says the acceleration of a falling body near the Earth's surface is 9.8 meters per second per second. If the body has a downward velocity v sub naught at time 0, what is the velocity at time t? Okay, so here's what we've got. We've got velocity as a function of time. This is the guy we need to see, or we need to find here. Now we do know the acceleration as a function of time is 9.8 meters per second squared, just like that. And so this right here is the derivative of velocity. So going backward, we get 9.8 t for the velocity, plus some constant that we don't know what it is. Okay? So this right here, though, this constant must be the initial velocity, right? Because this is how velocity is changing. This is the initial velocity. Okay. So what we're going to do is I'm just going to rewrite this as velocity as a function of time is equal to 9.8 t plus v sub naught, where this is the initial velocity. So when they ask what is the velocity at time t, well, this is our velocity. Okay, now the second part says if the position is x sub naught, so if the position is x sub naught at time 0, then what is the position at time t? Okay, so again, we need to work in reverse. So position as a function of time is the antiderivative of velocity, working backward. So the antiderivative of velocity is going to be 9.8 t squared over 2 plus v sub naught times t plus some constants of the antidifferentiation. So this is 4.9 t squared. This right here is just v sub naught times t, the initial velocity times time, plus, now, when t is 0, the position is x sub naught. So this guy, s at 0, should be equal to x sub naught, which means if I plug in 0 here, my constant is x sub naught. So overall, our position as a function of time is equal to 4.9 t squared plus the initial velocity times time plus that initial position at time 0. Okay, and this is right here. This is all that we can do with that particular function.